Hello everyone, welcome again. It's the second class of linear algebra with Python. Last week we have done mostly vectors and lists and for loops and functions, basics of Python and its application of linear algebra. So my fundamental vision with this short course is to help you understand the basics of linear algebra that is essential for deep learning while teaching you the Python tricks and the core ideas of Python. As I said, last week I have talked about uh, lists, for loop, basics of functions, and we have used that, like, for example, nested lists for matrix representation. But many cases, it can be optimized, okay? And when you become an AI engineer in the future, or when you write codes in general, the optimization is very important. It's an important skill to understand and grasp. So we will explore a few of these techniques, as you can see on the screen: list comprehension, generator expressions, zipping, argument unpacking, nested list comprehension, and lambda functions. Uh, you will see that you can actually implement, like, do everything without this. Okay, again, but this is used for uh, optimization. I will give you a simple example, a very simple example. Let's say you're calculating a sum of elements of a vector. Okay. So when you're calculating the sum of elements of a vector, what do you need? You do not need to store the entire list. You just need individual elements iterating over and over again, right? You need A, let's say it's A1, A2, A3. So you need to store A1 plus A2 plus A3 and iterate it. You do not need to store A1, you do not need to store A2 individually. So that's where the generator expressions come in. Okay, not the list. So mostly it's because of memory constraint and computational constraint to optimize these two parameters. There's something called dictionary, which we are not learning because it's not really important for linear algebra. But in the future, we will see that dictionary is really helpful for storing data in a different manner, keys and values. But we are not doing that. We will do this top things list comprehensions, zipping, generator expressions. You can see that using one line of code, you can just transpose a matrix. Okay. Again, just to remind all of you, we are doing from basic code lists. We are not using NumPy array. The reason is that NumPy array automatically has all the library functions that we are actually building from scratch. So this actually helps you to understand how things are working under the hood. And in this class, we will do as much as we can. Next class, we will start from determinant, and we will learn something about recursion. So let's get started, guys, and let's start. So let's comprehension. So what is list comprehension, guys? So list comprehension is a way to mimic the vectorized thinking in linear algebra. So let's say you have a score list. Okay. So let's say you have a score list, uh, score, let's say 1, 14, 22, 45, and 67. So what do you want to do? You want to normalize the score with respect to the maximum score. Okay. So you need to normalize the score with respect to the maximum score. So you define a max score. So you define max of score. So you will get that print. If you see, I'm doing simple things so that you understand. Okay, it's starting. So you print the max of max 67, right? But we want to normalize it. So using basic for loop, what will we do? We will have a for loop. We will do I. We will iterate I over the entire list, and then we will divide each element by the max, right? So that's the usual thing. So let me write it for you for the first time. So for I in, for let's say SC in score, we update SC as, for SC in score, we update SC as SC by max. Okay. Um, yeah. And let's see if we can print it. The good thing is the thing is that if you want to create a new list, let's say if you want to create this new list, let's say norm score. Okay. So what you need to do is that you need to append this whole thing. Append every single time. Okay. So let's see. Just give me a minute. Yeah. Many people are joining right now, so I apologize for this. So the okay, so here is, I think there is a small issue out here. Oh, we have is the same name, so we cannot use that. Let's call Maxim. Hmm, I'm not sure why this is happening. Okay. Okay. So I will check why it's happening later on, but let me show you. So essentially, this is a pseudocode. Okay. This is the core pseudocode that we use for the for loop. We append it, but in generator, in list comprehension, what you do is the following. You do it in a single line. How do you do it? So again, we need the max score. I don't know why it's not happening. I have to check once. So let's see. So what do you do in list comprehension? Let's see. So in this, you see that you are creating a new list and you're appending it. You do not need to do this in list comprehension. You can do it in a right away in a single line. So how does it look like? It looks like something like this. So let's norm score is equal to, so you create a new list. I hope all of you can see it. You create a new list. Let me clear that out. And now you do everything that you do for, in this case, okay, the same thing. You divide it for each element. Now you will list it. Now we'll run it for, what you will do, you will run this SC over the list. Okay, let's see. This is how it happens. All of you understood this? So I hope. Okay, so I don't know really why this is not happening. Let me see. Just give me a minute. Why, right. Sometimes happens. Sometimes inside this there are always maximum. So I've written this code earlier. It worked. I don't know why it's not working here. Just give me. Yeah. No, it's happening here, not. It's happening here in the maximum. Uh, just give me a minute. Interestingly, it's working in the other one that I've saved. I'm not sure why this is not working here. Okay, let me restart it. Let's say maximum. Okay. Anyways, let me go to the tab where it's working actually. So I don't know really why it's not working. It's very weird. Okay. So as you can see here that the score list, it's a list and I'm defining the max. So this is the ideal way you define the list right away. And this is ideally would have done for loop. But here you can see that you are actually doing it by score and you're dividing it. So essentially, instead of doing the both, you're appending both the steps together in a single way. And this is what it's called list comprehension. Okay. So where you're not defining all the steps and doing step by step, but you're doing it in a single way. It looks good. That's the only idea. And yeah, and it works. All of you understood this, guys? This is very basic. This is just telling you or sharing a new knowledge. Nothing to learn here. It's like a new. All of you understood this, guys? Yes or no? Can you give a thumbs up? Okay. So now let's go to the next one. Generator expressions. I hope nothing happens here. Let's see. So in generator expressions, what you do is that, let's say you are using the same list expressions. Let's say you can create a list of, let's say you have a list of A is equal to 1, 2, and 3. Is it because there is a space out here? No. Anyways. And now you want to say that you want to do square. Okay. So you define SQ, and what you do is that you take each element of the array and you multiply with it for A in array. So I am using list comprehension here. Okay. Now if you print SQ, you get this whole thing. Okay. I use list comprehension here. I hope all of you understood, guys. Did you understand? So now let's say you're taking the sum of it. So you do not need all each of the element. You rather need 1 plus 4 plus 9. So when you actually do the sum and you need less memory, so let's say imagine it's millions of data, then it will matter, right? You don't need to store this. So what do you do then? That's where the generator expressions come. So generator expressions come from the usefulness comes from the aspect that you do not need to store this. So how to do that? Or how to do the sum actually? So you can actually do the sum in this way, right? You can do the sum like S is equal to sum of SQ, and then you can print S. Sum will be 14, right? And it's coming out. But let's say you don't want to save the list. You want to iterate. So again, for iterating, actually you have to save the list, right? So that's where the generator expression comes. Okay, generator expression comes that you do not save the list. How to do that? You do it by this. So essentially it's an iterative. So if you just print SQ, it will not come out to be a list. Okay, it will come out to be something called a generator object. That means it's a generator object which only saves the first one and it will iterate to the next. Okay, during computation it will not save the entire whole list. So this is where now you can do the same thing. Actually you can define S is equal to sum on SQ. So it's the same thing. If you see the list SQ is nothing but this. So I am using list comprehension inside generator expressions and expressions together. Both of them will give actually the same thing if you observe it carefully. Okay, both of them will actually give the same thing. But here it saves the list, because if you print LSQ here and if you print SQ here, you will see the first one is a generator object, the second one is the list. Okay, so it saves the list, but here it is a iterator. So it iterates, but it does the same thing. Now why this works? Because for the sum is nothing but an aggregate function. Similarly, you can do mean here, or can you? Can you do mean here? Yes. So you can do anything you want on a list. When it's an aggregation of that, when it's a function, aggregate function. But if you want to save memory, this is what you do. Okay, so it's a good habit to use this whenever you see that, and you will be aware of that. All of you got it, guys? This is a generator expression. Any questions? All of you got it? Can you give a thumbs up? Great. So now the next question. Okay, any questions out there? Any more questions? Any doubts? Okay, good. So the next question, zipping. So what exactly happens in zipping? It's very fun, and zipping is really one of the most important aspect in linear algebra. It really saves your time. So what does zipping do? Zipping is nothing but, let's say your v1 is equal to 1 2 3, and your v2 is equal to 3 4 5. Now let's say you want, so if you want to do zip of v1 v2, what is this? Let's see if we get something. What do we get when you print this? We print great nothing. But it's kind of an iterative thing. But you can print for x comma y in zip. Print x comma y. Let's see what happens. Can you tell me what it is doing? Anyone looking at it? Anyone? What exactly it is doing? Any idea, guys? What do you think? It's taking in two vectors. Yeah, it's a two-dimensional array, but corresponding to this v1, v2, what is this function doing? It's pairing what? Yeah, exactly. It's a column vector. Very good. So if you remember, last day I have talked about the very fact that when you represent a matrix, okay, when you represent a matrix, you have rows vector and the list of rows. So it's kind of a row view. Okay, you only have the rows like this. But what if you want to do the columns of that? What if you want to understand the columns? Okay, so how to think about that, how to do that? And that's where we use zipping principle. Okay, so let me go back here. So if you observe what zip is doing, and this is very important, so please be careful here. Zip is nothing but extract this 1 3 2 4 and 3 5. So 1 3 2 4 and 3 5. You can actually use zipping for vector addition. Okay, so you can actually do zipping for vector addition, but zipping essentially it's iterating, it's creating a pair of the ith elements of multiple vectors. Okay, it's creating ith element of multi. Here you're doing 3. Let's say, can we do v3? Let's say we define v3. 6 7 5. Let's say, can we do v3? That's a good question to ask. So I'm sure it will happen. Yeah, so you can see now it's creating the columns of this together. We will learn to extract this, move into list, and do our transpose operation later on. But zip exactly does this. So what is an example? We can use a vector summation. Okay, we can use vector summation, but the interesting thing is that we can also change into list. Okay, as I said that we cannot print this. But we can transform this zip into a, so you can see now it's nothing but this. But although inside of this is, remember, inside of this is again a generator. It's not a list because of this first bracket. Okay, so these are very minute, subtle things. The meaning is the same, but how it's stored, it's different. Okay, and yeah, that's very important to understand. Okay, so did all of you understand zip, guys? Yes or no? Can you give a thumbs up? Do you have any questions? So the zipping principle is very important, and we'll use this, apply this in our linear algebra computations. Okay, very good. So now the next question, next aspect, that is the argument unpacking. So what exactly it is doing? So argument unpacking is nothing but it's extracting arguments from a list or a generator. Okay, so what does it mean? Let's say you have a list 1, 2, 3, and you want to print star of LST. So what does it do? It extract this. So it's extract 1, 2, 3 out of the list structure and put it as single variables. So let's say, what if you want to do it in in a matrix format? Now you will see why this is useful later on when we apply this mostly, but I'm telling you the knowledge. So this is a matrix, right? So can someone tell me what is the dimension of this matrix? 2 cross 3 or 3 cross 2? 2 cross 3 or 3 cross 2? Yes, 2 cross 3, because there are 2 rows and 3 columns. Simple. Okay, Kaustav has asked me a question. I really like question. So let me look into the questions. Yeah, thank you, Yash. Thank you, Arnav, Shuhani, and Harish. So is an algorithmic way we do zipping then argumenting? I don't. Yeah, so these are all done in C. You see, these are basic things, right? You can really understand that. So these are actually for loop in an optimized way under the hood, but they are done in C, let's say. Okay, C++. So that makes it faster. So the whole idea of introducing this is optimizing the code behind, which is C, the optimized way of coding in human format. And that's what is building. So essentially, we are using that C power in this optimized way. That's it. Okay, so the next one. So this is a matrix. Very good. This is a matrix M. And now what we want to do? We're gonna look into print of star M. So can someone tell me what it will come out to be? What is the idea? So essentially, it's nothing but unwrapping the elements in a list. Okay. So it will nothing but come out to be the list inside, the rows. Now, why this is important? Because it will help you to extract. If you want to operate on this, it will help you to extract this. And you will see while doing transpose how it's important. Okay. You will see this. Okay. This is basic stuff. And this is not really, I didn't provide an example like where it will be useful. But I hope all of you understood. This is basic stuff. This is no hard and fast stuff. So what is a nested list comprehension again? A matrix is a nested list, right? You have already seen this here. A matrix is a nested list. So it's like nothing but the list comprehension here, which didn't work, unfortunately. But it's in a matrix format. Okay. So let's see what we can use. So the basic pattern is this. The basic pattern is this. It's inner loop for outer loop kind of thing. So let me give an example. The basic example is, let's say you want to create an identity matrix. How do you create an identity matrix? If you want to create an identity matrix, ideally you have to do this. Okay. So let's say you want to create an identity matrix, ideally you have to do this big function. Okay, and it'll create an identity matrix. Okay. Yes. This is the big function. And this is what the list comprehension is all about. So what it is doing, let's try to understand this. So, okay. So let's not go much deeper into it. Let's understand it. That, like, let's not rewrite it again and go into the depths. Let's understand it because you already done list comprehension. So you can see what it's doing. It's creating a new function. Okay. So here it's appending and it's appending if within a certain if condition. So there are two for loops and one if loop, right? There are two for loops and one if, not loop, but if condition. So it's combining all of them together in a list. So you rewrite the condition that, so essentially it's an inner loop it's creating. So when you essentially what do you do? Nested list comprehension is nothing but you create a new list, right? So when you create a new list, in this case it's a nested loop. So there are two lists. One is the inner list, that is the inner loop, as you can see, and one is the outer list. Okay. So the first is that you create the inner list, and then there is a for loop in the inner list, and there is a for loop in the outer list. Okay. So what do you do? How do you create the inner list? Let's not look into that and try to do. One, if the ith I is equal to j, else 0, right? One if I is equal to j, else 0. So inside what we are going to do, it will be 1 0 0, one list, the row, the next one will be 0 1 0, and next one will be 0 0 1, right? This will be the rows. So what we are going to do here, one if I is equal to j, else 0 for j in range 3, for okay, so again, if you have forgotten, you should remind yourself this, that what is the I and what is the j here. Okay, this is from the first lesson. The I is the, so j is what? J is the column and I is the row, is it? So let's revisit it again. M of 0, 1, or M of, yeah, what it is, 2. So what is 0 here? 0 is the first row. So M of 0 is nothing but the first, the first element in the list. That means the first, so this list, the outer list is nothing but a list of rows. So M0 is nothing but the 0th row. So the first is nothing but M0 is nothing but the 0th row. So the row ID. And the next one is the column ID. Okay. So I hope all of you remembered it. So now let's go back to here. So what exactly is happening here? So when you do I, so let's understand this very carefully. When you do I in range in the letter list, it's nothing but creating the list for the number of rows. Okay, this is the number of rows. Okay, the I is the number of rows, and this is the number of, j is the number of columns. So that's why actually it's not understandable, because both it's an n dimensional, like n cross n, right? So you're not understanding. That's why I have to explain it so much. So here I is the row and the j is the column. Okay, so in each of the inner list, it's a condition, it's a row, right? And it's a single row, so the row element is constant, the column element is varying. Okay, 1 0 0, the column element is varying because the row is constant. So therefore the j is, you have to vary the jth thing. So that's why one if ith rows, ith element is equal to the jth element, right? So that's what it's doing. I hope all of you understanding this. I'm not making it complicated, but I really wanted to understand this. So this is what it's doing here. And then it's reiterating over the next range, the number of rows, as you can see here. All of you understood this, guys? Yes, no? Great. So yes. So the ith is the row and the jth is the column. Okay. So just you have to make sure that actually here the I and J really don't matter in that sense, but we do it for our mental purposes. Okay. So even if you do J is equal to I, so what happens? Here in this case, n cross, since it's n cross n, it will be the same. But for other cases, you have to be careful. Okay. 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 So this is all about nested comprehension. I have sometimes a tendency to go very deep into it, but I'm not going into it because of the time length. So what is lambda function? So lambda is nothing but, okay. So again, it's just like when you define a function, you do def function return. Let's say when you define a function, you do def, let's say f of x, x is equal to x plus 1, return x, right? Let's say you're doing, take a number and return and add 1 to it. Now you have to define this function, right? And save it. But let's say you want to do it on the fly. Okay. So that's where you would call lambda. So lambda x, so essentially if you remember how function is defined like this, x2. So if you remind, function defined like this, right? F from R to R. So it's kind of motivated from that. So lambda is a function, is defined from x, and the output is x plus 1. Okay. So in that motivation, it has been done. Now, why it is useful? It is not useful, like it's useful because it helps us in saving time and doing small functions on the fly. Let's say you want to do quick x square. So let me give an example. This is an example is required. First of all, how do you access this function? This is a function in itself. Okay. That's why it's giving output to this. How do you access this function? This is a function itself. So we are not defining anything. So this is a function now. And then you are applying it on 2. So this is now a function. This is how we define the function. And now this part is the function and this is the argument. Okay. So now let's go into these are simple things, okay? These are not extremely new knowledge. So now let's say you have a list. Now you want to do on 2 things. You want to do select the, let's say, okay. Let's make it a bit interesting. Yeah. So now you want to select that number which is closest to, let's say, 12. Okay. So closest to 12. So what do you do? Remember again, these are not when you do in other cases, like let's say you want to find the minimum of this. That's possible. But let's say you want to apply a function on this, you cannot on each of the element. You cannot really do it like using a single function. It can happen in NumPy, but in list it doesn't happen because you have to define it from scratch. Okay, so that's where it becomes useful. When you define a new function, you can define a function and then do a for loop each element of the row. Now let's say you want to find that. So what you do is that what you can find the minimum. Okay, use nums. But here what you are finding the minimum to, you're not finding the minimum in this, but you are finding the minimum over the difference between of each of these elements, the absolute difference between each of these elements from 10. Okay, even you cannot do nums minus 10, right? You have only access to each individual element. So there's another option in keys that is called, so in this keys you can actually apply a function on each element, and that's where the magic happens. So what it is doing, this is taking each element Applying this function, this is the key, what the key is doing. Applying this function each of the elements. Okay, applying this function on each of the elements and then taking the minimum of it. Yeah. So now it says it can be 9, 2, but it took this because this is, yeah. So because this is earlier, as you can see, we changed it, so it gave 9 now. So I hope all of you understood this. So now if you wouldn't have done this, you have to define a new function that actually applies this absolute x minus 10 from each of the elements. That is what saves time. Okay, so this is the optimization of all these things. Similarly, you can do it on sort if you want to sort the array. So what you can do, you can apply the function sorted on nums. Again, use the same key. And you can say it's sorted now. Okay, so essentially what it does, it saves you time and space. Again, these are all optimization, so this may not be so much interesting, but now it will be interesting because we will be applying these techniques, these ideas to vectors and matrices. So we will be doing a few applications. In first, we will start with the application of a vector application, that is cosine similarity between two vectors. So what is the cosine similarity between two vectors? You take two vectors, do the dot product, and divide it by the corresponding norms. Okay, so let's define it. So def, you can do by lambda function, or not, it's not required here. Okay, it's only, remember, only use lambda function when it's a short function and you want to do it on the fly. Okay, that's when you use lambda function. That's it. Because for x square, for absolute value, you do not need to define another function, right? Let's say you define a short function. That's how you do it. Okay, that's why it's useful. So do not overdo it. So that's why we will not do lambda here. So let's say you want to do cos sim between two vectors a and b, or v1, v2. So let's first define v1, v2. 1, 2, 3. That's my generic one, and v2 is 2, 3. What is Google Colab? Oh, okay. Yes. Yeah. I'm using Google Colab. So now let's say I'm defining this. Yes, you're right. I'm using Google Colab. So we need to calculate the dot product. So now this is where it's coming. Remember, what is dot product? It's nothing but you have two vectors. You are doing element-wise multiplication and adding it. Now, can you tell me what can be used right away? When you do element-wise multiplication, which property I told you comes right into the mind? List comprehension, generator expression, zipping, argument unpacking, nested list comprehension, lambda function, vectors. Which comes to your mind, guys? When you do element-wise multiplication, which property comes to your mind? Any idea? Where do you do element-wise stuff? Which of the properties does element-wise stuff? Yeah. Do you remember it? Zip. Very good, Arnav. Thank you so much. Zip. So exactly. So it's zipping. But again, when we zip, we will get each of these elements, right? But we need to multiply it and sum it. And we do not want to save this in a list, in a single list. We want to do it right away. And that's where generator. So this is an application of list comprehension, zipping, and generator expressions. Okay, so let's see. So what we will do, we will do sum. What we will do, we are multiplying x times y for x comma y in each of the v1, v2, right? So zip of v1 comma v2. So for v1, v2, we are getting each of the xy's. We multiply it. So this gives, ideally would have given you a list, but we do not want a list. We want to save space. And that's why we are generating generator expression because of this. And then we sum it. So, and we can directly do return. And you can see it happen. So it's so quick, right? All of you understood the power of it. It's very simple and you can understand it right away. So we do not have to do a for loop. So this is, again, this is dot product. Okay, we have to do something more. So that's why we define norm1, which is the norm. Again, we will use the same thing. We will use again the general expressions. So what is norm1? Norm1 is the sum of squares of each of the elements. So it's a square for a in v1, right? And norm2 is sum of, let's say, b square for b in v2. And then you divide this by norm1 times norm2. Oh, I did a small mistake. Now this sum is sum of squares. We need to do a square root of that, right? So this is all about it. All of you got it, guys? Did you understand why this is useful? So this is an application of list comprehension, zipping, and generator expressions together. Very good. Now you will see how we can do things very quickly. Now let's do matrix addition. In matrix addition, we will need nested list comprehension and zipping. Okay. So how do we do that? Let's get started. This is important. Okay. So we're going to define a new function, def add a comma b, two matrices. So let's define those two matrices, m1 and m2. So I have already saved it, so I will not. So this is the definition of the matrix. Sorry. Now let's define def add a comma b. So we are defining those two matrices, like inputting the two parameters a and b, and observe that what's happening. Understand, this is a really interesting thing. This is where you will understand better nested comprehension and zipping together. So what do you want? Very careful, okay? Very careful. So when you add, so you have to do always two for loops, okay? That you have to understand. In the first for loop, understand, you get the rows, each of the rows, and the second for loop, you will access each of the element of the rows. Okay, so when you do zipping, how can you do zipping? So in the previous one, if you see, this was how we added two matrices. It was a lot, right? We essentially accessed each of the elements and added them together. Now we'll do the same thing over zipping. Okay, so how to do that? Let's understand it. First, if you remember the nested list comprehension here, we access the inner loop and for each outer loop. So this is how you access each of the inner loop elements, right? So let's get started. Understand this very carefully. For each inner loop, so when you say okay, understand what you want. Okay, you want the row, each row list. So I'm just writing a few things so that you understand. So zip of row A and row B. So we need two things, row of A and row of B, and zip of. So this is actually a hierarchical structure. That's why I wanted to understand. When you do zip of A of B, actually you have to do from outer to inside, not the other way around. Okay. So that's why it's a bit hard when I am trying to go from inside to outside to explain to you. So first understand the outside loop. So when you do zip of A, what will be the output? When you do zip of A and B, the output is each of the list of this together, right? So let's do step by step so that you understand this better. Let's do print of, so zip of A. Okay, M1. I would sell this. Yeah. So when you do zip, it's coming out to be this. Oh, it should be, sorry, I'm so sorry. Like this. So you're doing this, when you're doing this, essentially you are taking each of this together, right? So when you do zip of M1, M2, it's a list of a pair of the each rows. So row A and row B, the corresponding rows. Now you can access each of those row A and row B and then add each of them together. That's what it's doing, right? So essentially what we are going to do is to add two matrices. We are accessing each row pair of M1 and M2 and adding those rows. Okay. Now adding those rows again needs another adding those. So again, repeating. When you are adding two matrices, you're first accessing rows of each of those matrices, pairs of rows of each of those matrices. And then again, when you access those pairs, you're again adding those two row pairs using another zip. So this zip of the matrices is happening in the outer loop, and the zip of the inner rows happening is the inner loop. All of you understood that, guys? This is very important. So let's do it. So let you do def add A comma B. That's why I was finding a bit difficult to explain to you what I was understanding, but this is the way to understand. First, look at the outer loop. So let me not rub it, erase it. Zip M A comma B and zip A comma B and zip of row A comma row B. So this gives pairs of rows in outer loop. This is very important to understand, okay? So that you can use it freely. And this gives pairs of elements in inner loop, which is nothing but the pairs of rows right now, the rows. So now you define def of A and B. So let's define the for loop of the outside. So for row A comma row B in zip of A comma B. This is the outer loop, okay? So you define a list for, so this is very important. Now, this is the outer loop. Now you're defining the inner loop now, okay? For, now your row A and row B are there. So what you're doing, now you're accessing each of the elements of those rows. For A comma B, remember you have two vectors. When you have two vectors and you do zip, you actually access each of the pairs of the elements in zip of row A comma row B. And you're doing for each of the elements, you're adding those elements. And you return this. You print. And you have this. All of you understood this, guys? This is very important to understand. This is, I think, this is the best example for you to understand and learn about listing and zipping together. Okay, matrix, because it has two layers of, two layers. Is this clear, or do you want me to listen, explain once again? So first, when you want to do zip of multidimensionals, you want to think in terms of outer loop first, and from the outer loop you're getting the two rows, and then the inner loop. When you get the two rows together, you get each of the elements of those rows. Is it clear, guys? Can you give a thumbs up if it's clear? This is very important. Otherwise, if you do not understand this, you will not be able to apply zip in a large scale scenario. Okay, I only see one hand. So Agnik, Arnav, Gauri, Reem, Shuhani, and Yash. Any questions? Is there any way? Okay. So were you present, Agnik, during zipping and the nested? So let me explain it again. I know it's a bit, it's two layers of abstraction. So, okay. So let's say, first, when you do M1, M2, so what you're getting, when you do zipping of this, you're getting this. So let's print list of zip of M1, M2. So this is accessing the rows, the pairwise rows. Of M1, M2. You can see it's a pairwise rows. You can see it together. It's pair, right? I hope you can see it. It's pairwise rows. Now you want to access each of the rows. So let's say you take the first rows. So this is the first row. Okay, let's look at it like this. I'm printing, that's why it's becoming horizontal. This is the first row. Okay. The first row inside that list. So now you want to do what? Now you want to access each of these vectors together as a zip. Now you want to access 1 and 2, 1 and 1 of this. So you now look into this list of zip of the rows in this and this. How do you do it? For A and B in zip of okay, let's see if it works like this. I'm not sure because it has already transformed. Okay, can we access this somehow? Just let me check once. No. Okay, just give me a minute. Okay. Let's see if we can do like this. Sorry. Yeah, there are too many things to. Yeah, I know, because essentially we're trying to access this. So now what happens? You have access to this, okay? So what you want to do now, you want to access 1 and 1. So you're doing A plus B for A comma B in zip of this, the first row. So that's what you're getting. So you're doing two layers. I hope you understand now. So you're accessing the two outer rows, the two rows in when you do the zip of M1, M2, and when you do the zip of each of those two rows, you get the element wise addition. Okay, because you're accessing each of the elements now. So the inner row is accessing each of the inner elements, and each of the outer row, like When you're doing zip of M1, M2, it's accessing each of the rows out there, and each of the now it's accessing the element of the row. So essentially, what we are saying, what we are doing here, this addition is nothing but addition of the rows of the matrices, addition of the corresponding row of the matrices. You can see that. Now, did you understand? So now see this, observe this very carefully. When you're doing row A and row B, you're accessing the corresponding rows of zip of A and B, like A and B, the corresponding rows. And now when you access the corresponding rows, you take them and you access the corresponding elements of each of those rows and adding them. So it's row addition, you can say, in some sense. All of you got it, guys? Agnik, did you understand? Okay. Yeah. So yeah, this is a bit abstract because we are used to read from left to right, right? That's why it's happening. Actually, it's happening from right to left here, the operation. That's why it's becoming a bit difficult for you to understand. So whenever you're doing this multi-level thing, you in zip, you're actually doing it from outside to inside. So remember also when we access this when you did this in for loop, first we actually accessed, yes, so I is in the rows and j is in the columns. Yes, ideally we should do I in the number of, yes, the number of columns, yes, number of rows, yes. So exactly we are doing the same thing here. Yeah, just go and think about it yourself. Okay, so now the matrix scaling, I think you should do is the homework. I should tell you now the transpose, which is the most important aspect. Okay, so the transpose of a matrix, the transpose of a matrix, how to do it fast. Let's see. So again, there's a matrix. This, what do you want to do? You want to make a transpose of it. We've already seen before that if we do the zip of this, not zip. Yeah, remember zip is used for, yes. Just give me a minute. Zip is used for when you are trying to do multiple, elements together. Now, when you do zip, understand this very carefully. When you do zip, you need multiple vectors, right? Now, here actually each of the rows is a multiple vector input to the zip, right? Each of the rows is a multiple vector input to the zip. Do you understand this, guys? Then only you can X out. So, for example, if I do zip, then it will come out to be all the vectors. Do you understand? We need to access each of those elements. So I would say, so this is not matrix scaling, I'm sorry. So this is what it transforms into the rows into columns. 1, 2, 4, and 7 is the first one. So now we want each of the rows as input to the zip. How to get access to each of the rows? That's where the arguments come in. Okay, that's where the arguments come in here. You can see the argument unpacking. So argument unpacking was nothing but accessing each of the elements of a list. So we are now accessing each of the elements of the outer list of matrices. Okay, so now how to do this? It's simple. So again, let's look into argument unpacking. So if you want to do star of matrix, what does it give? Oh, I cannot print star like this. I'm sure I can. Yeah. So you can see star of matrix gives each of them as a single arguments. That's a good idea. So now what we will do, we will combine them these two, right? A new one. We need the rows to be arguments of zip. Argument unpacking. uses transforms matrix into the argument, the rows argument. So now you can see, if you want to see list of zip of star of matrix, then you can see it becomes this. But again, there's a problem here. The problem is the inner thing is not a list. Okay. So that's why we need another small step. And again, we will use list comprehension here. So we want inner list to be a list. So when you do list, it automatically does it. But we want each of the elements of this to be a zip. So we do list of each of the columns that are happening for column in zip of star matrix. So when zip is automatically in iterator, right? So let's see what zip is. As you have seen, zip star of this is all of them. So it accessing each of the columns now and transforming into list because each of the inner elements was not a list. And this is now the transpose. Okay. If you look into transpose, it looks beautiful now. List of list. Now it's a matrix. So do you understand the beauty of this? Using a single line of code, you can make the whole transpose by using zip and argumentations. So that's why these are powerful elements that can optimize your process of defining things and making things happen. All of you understood this, guys? Yes or no? Yes or no? Yes. Good. Great. So now we can try to do matrix dot product. Again, it will be nothing but a simple applications of all the zipping and things. So it's a matrix and vector dot product. So let's try to do it. So this is a matrix and vector. Okay. So we want this 1 times 1, 2 times this. So let's see how will we do it. Again, think about it. The first one is a matrix. So what do you want? You want the dot product of this with this, right? So you want to access the rows of this, right? So how to access the rows? How to access the rows? Just follow the rows. So take the outer loop first again. So for row in A, you want the dot product of this and X, right? So we have previously defined dot product, but let's do it from scratch again. So dot product is nothing but sum of, so we are using generating functions, generator expressions here. A times B for A and B in, now you use zip. Because zip are taking A and X together. Sorry, it will be row and X. So now this will turn out to be, for each row, it will turn out to be a single element, right? Like this. So now it turned out to be this. All of you understood this? So simple, right? If you just know the proper technique, you will get out this. Did you understand this, guys? Any question? So we are using iteratively zipping and list comprehensions and again, generator expressions. Okay, so now again the matrix multiplication, this is the fun part. If you remember last day I told you, if you remember carefully, that a matrix multiplication is nothing but if you take the rows and the columns, essentially it's A times B. If you take the matrix multiplication A times B, essentially it's nothing but the A times B is, let's say, C. So Cij is nothing but dot product of ith row of A and jth column of B. This is the basic idea. Okay. So now again, Here you can understand that dot product is nothing but this. Okay. Dot product is nothing but generated expression plus zipping, simple, of this, the ith row and jth column, right? The element. So therefore, um, yeah. So now the thing comes in terms of when you are defining a new matrix, you have to think about the output. The output is a list of list again. So you have to first make the rows. Okay. First make the rows and you have to make it properly. Okay. So that's where it will be list comprehension, because you need to make the rows like this. Okay. Just like this. So essentially why I did it this way, because this will is nothing but the first row of a, if x is the column of the bth matrix, the first bth matrix, this is the corresponding row of the a times b. Okay, that's why it's coming out to be like this. So this will be actually, so this is nothing but, what I have done here is nothing but the inner loop. Okay, and there will be another aspect for the outer loop. So let's do it. So let's first look into the columns. Let's first look into the columns. So I have I need to define the matrices. So here is A and B. So let's now look at the columns. How can I access the columns of B? So we need the columns of B, right? So columns of B is nothing but zip of star B, right? This is the argument of B. We have just done it, right? Zip of star B, star matrix. So we need the list. So let's say, just to remind you, so this is what it looks like. Okay. The columns 7, 9, 11, 8, and 12. Okay. So now next, we now need, we have already got the columns, right? So now we need the matrix multiplication. So def matmul a comma b. So what we're going to do, think about it carefully. We need again two for loops. So first we define the dot product. So we already defined the dot product here. So we are now defining the inner loop. So sum of x times I times j for I comma j in zip of the two rows. The row, the ith row and the jth column. Sorry, I am doing again a mistake here. Not the two rows. These are the elements of. No, yeah, it's correct. Let's not name it that, so it will be confusing. Oh, yeah. The corresponding rth. So these are two vectors, right? One is the row vector, one is the column vector. So here is nothing but it will be row of A and column of B, right? It will be row of A and column of B. We can call it AB. We are taking the dot product of it. This is the dot product of row A and column B. Now for the row is coming from the list of, for the row is coming from the list of, I think, yeah, there's a sum here. just, I think I am, yeah, the sum is here. Okay, I did a mistake. Yes, sum is the, so this is the sum. So this is the dot product, right? So now what's happening? We need to get access to the row. So for row A in, for row A in what? In A, because each row is a list of rows. Yeah, the element of A is a list of rows. And for column B in, now we again define the zip of star. We already defined the columns. So zip of star B. And we make it into a list. So we can have multiple. So it creates the inner list. I have done a small mistake. This is important. So we have to create an inner list. So this is where I have done one mistake. So the inner list is nothing but the first row will be the inner list, right? Let's say. So the first row is nothing but the ith row and all the columns. So it's iterating over the columns to get the first row of the output. So it will be before this. Did you understand, guys, why I'm doing this? The first row, any row, when you're multiplying columns, so row I of C is equal to AB, A times B, is nothing but the dot product, like the sequence of dot products of ith row of A and all the columns of B, right? So that's why we have to, the inner list is that. So that's why the inner list is the rows. So we are therefore iterating over all the columns of B and doing the dot product with the ith row, and then we're iterating over all the rows of A. Make sense, guys? So now you got this, right? It's simple. So yeah, so I think this is it. You can do matrix mean by row again using your own idea. Next day we will be doing matrix determinant, matrix inverse, and eigenvalues. So why next day? Because we will use generalized determinants. Okay, one important thing is here that I wanted to tell you is for the adding of a matrix. Okay, for adding of a matrix, you can actually, in this case, do multiple matrices. Okay, and there's a way of that. For multiple matrices, let's try to do it. So let's say you want to do it for multiple matrices. Add them together, let's say M3. Not really. After this, we will just, so once we are done with this, we will move on to NumPy and Torch. The reason is that I wanted to tell you about all these things because I want you to be comfortable and understand that working with list and its operation is very important, okay? It's important for data pre-processing in AI. Because data preprocessing will happen in this list format, you have to transform it and all these things. Dictionary and list are all important. I have not done dictionary. For example, in EOLO, in computer vision EOLO, the data is input into the data loader in AI as a dictionary, okay, to save space. So you have to understand this. Without these basics, you will never understand what's happening out there. For example, in batch-wise In dictionary, dictionary is very important because it helps you understand also many things. It saves space, memory, and yeah. So in the data loader, it's a iteration, it's a batch wise iteration, right? So in that batch wise iteration, you have to put key and values out there to extract the iteration. So list really gives you mostly the generation, zip and the generator. That gives you a really good understanding. The zip, mostly the idea of the iteration. What is an iterator? It's very different from list. Okay, it's iterates one by one. So this is very important in the Python framework. um Not in linear algebra. We will not need them in linear algebra, because after linear algebra is complete, I will do a medical imaging and imaging thing. Okay, because imaging is nothing but a visualization of the matrix. And then I'm planning to. So this will take around the end of April, till the end of April. And in the end, in April, um, in May, I am not sure what I will do. But I have a plan to start generative AI and LLM, because I have a talk at ISI, and also when I'm going back to India during June, I will be giving, we will be doing courses at ISI, so I can do that and again come back by the late of this year on dictionaries and deep learning. If I get time, essentially my goal is to teach you the entire of deep learning and everything from scratch, the basic core needed thing. But dictionaries, I think dictionary just needs 15 minutes of a class more, not much. Okay, so so let's just do the final thing that we need to do is the matrix addition. Let's say you want to do multiple matrix addition. Okay, how to do that? When you want to do multiple matrix addition, uh, again, it's a very interesting thing. So let's see. So def. So when you have multiple matrix addition, you have to understand that. Just give me a minute. Let me think. Def, let's say. Mm, just give me a minute. Mm, yeah. I think it's a very same thing. Let's try it. So let's add M1, M2, M3. So what you're doing is that, again, it's the same thing. You can return A plus B plus C. So this is where it turns valuable. So we do not want to define is A plus B. We like when it's multiple matrices, you have to think in terms of all of them together. So will be sum of, so first the inner one, sum of values. Now these values are in, so these values are nothing but the let's say the ith rows of all the matrices. say in zip of all the rows. I'm trying to write the pseudo code. So it's zip of all the rows, okay? So the good thing about this is if you know all the rows, okay. For rows, now where will we get rows from? The rows will be got from the zip of the matrices, right? In zip of matrices. Now the matrices is not there. So that's how we will get this. Now let me think. Um, okay, so yeah, so this is a basic idea. When you don't want to do multiple things, this is exactly how it's happening. Now I'm thinking how to get the star of the matrices. I think the good thing about when you do star of the matrix, it takes all the things, yes, together. So I think that's the best part. Add of M1, M2, M3. Oh, M3 is not defined. Oh, I didn't run this. Oh, let's say add 2. Yeah, exactly. So you can actually, yes. So this is the whole idea. You can actually also add M4 if you want. Just defined M4 is equal to M1, let's say. Yeah, and you will get this. So the basic idea is that you can translate this whole thing. You don't have to write row A and row B, you just write star rows. So the star rows, star matrices, in whatever input it gives, it will be fetching them as okay, this makes sense. So whatever, so essentially, yeah, so this is nothing but a set of inputs and it's taking them as all as arguments. Yeah. Oh, yeah. So yeah, perfect. This makes sense because star is nothing but the argumentation, right? The argumentation, it unpacking, argument unpacking. So it's unpacking this input as a set of arguments. Well, all the, of course, this is the input in itself, but you can see rows here. These are actually in a list format, right? So rather, yeah, as a element format, a code element block format. So it's converting them as arguments, and that's how it's doing really good. So zip needs, yeah, this is really good. I hope all of you understood this, guys, right? Yeah. So this is very important, and I will leave you. Thank you for staying. It's 1.5 hours. I hope you enjoyed this, and I will see you in the next class with recursion and determinant. We will probably use this concepts from today's class, and we will absolutely thank you, Sohani, and others. And next day we will be teaching that, and we will probably talk about. I am not sure. It depends upon my schedule, and I will talk about NumPy and Torch too. I will complete NumPy and Torch. I think that's the end of it. Then we will look for more. Thank you guys. Bye bye.